So next we have a talk on loop verification with invariants and contracts, which is from Gidon Ernst. So hopefully you can share your slides.
It should work, and you should also hear me now.
Yeah, we can see your slides and we can hear you.
Great, thanks. So welcome to my talk, Loop Verification with Invariants and Contracts. Before I start, let me just put this work into context. So this is about deductive proofs of strong functional specifications like sorting and searching and the like. And let me start with offering two entry points for this talk. So the first entry point is a folklore saying that as recursive algorithms are easier to prove correct than iterative ones. Maybe you believe this or maybe not, I'm not so sure, but I certainly have heard this before. The second entry point is this nice tweet. I'm trying to do it so that my whole logic automatically knows how to turn while loops into recursive functions. Has anyone done this before? And I think this is an insightful question that refers to this folklore quote. And indeed, of course, people have thought about it a lot. So for example, Eric Hinner's specified blocks, or maybe you've seen Thomas Turk's paper on local reasoning about while loops. And this paper is about the same issue. And there are tool implementations like whole foot or maybe very fast or key. And this feature is essentially available in all general purpose interactive theorem provers that are used to verify software. Now, if you have ever taught such a rule for while loops, then please write that into the chat. I would be interested in that. But it seems that most people actually don't think about what that means and don't use this kind of approach. So this is the standard whole logic while rule. We have an invariant that is defined over the, say, set of variables of the program. And given that the invariant holds now and some premise, you prove that the conclusion is after executing the loop is that the invariant still holds and you have the negated loop test. And this is somewhat a canonical conclusion because you have no control how to instantiate it, right? And the idea of treating while loops as recursive procedures is to replace this canonical conclusion by a relational summary, which I'm going to call R, which is sort of like a postcondition that takes two parameters. This x0 refers to the state back before the loop, which is captured here by a logical variable. And x, of course, in the post condition refers to the final value. So a contract consists of an invariant and such a relational summary. And let me just say that it is crucial that it is a relation for the approach to work. And secondly, it is this first argument, the x0, that moves across iterations in contrast to the invariant, which moves this argument x. And I will explain how. But first, let me convince you that this is worthwhile. So basically, this already gives you a theoretical explanation why you should use contracts and not just invariants, right? Because you can, it's strictly more general. But let me convince you with an example. So I will start with this nice algorithm. It's called finding the maximum by elimination. It's taken from the Verify This competition from 2011. And the idea is as follows. So we have this array here, for example, with 6 numbers, and we want to find number 9. And we do this by keeping two indices, one for the left, one left index and one right index. And we are gradually moving them inwards until we find this number 9. And the way we do it is we just look at the two current numbers, 8 and 4, and then we move the pointer, which is pointing to the smaller of those numbers. So we exclude number 4 because 4 is smaller than 8. And for the same reason, we can exclude number 6. And now we observe that this time we have to move the left pointer because 8 is smaller than 9. And at that point, we should take a break and think about, because this nicely describes the intermediate states of these algorithms, which of course then will explain how the invariant might look like. So we have in the middle a range of potential candidates that are still being examined. And on the left and on the right, we have ranges of elements that are already eliminated because we have some justification that they are too small to be a good candidate. And of course, either the number 5 or the number 9 is this kind of justification. And if we can, so we can write this down more explicitly. We can say that the maximum of the two boundary values, 5 and 9, dominates all of the excluded elements, right? So if we continue, then next we exclude the 5 and the 1, and then we have the 2 pointers pointing to this residual element, and of course then we can find the maximum value here. So let me prove this for you. At least let me show you the specification that is necessary to prove this. And I'm starting with a recursive algorithm because the baseline against which we compare is from that quote, is that recursive algorithms are supposed to be easy to verify. And so is the case. So we have this algorithm. Let me just briefly explain the code. So we have these 3 cases down at the bottom. Either we are in the base case and we have found the maximum, or the right index is greater than the element at the right index is greater than the element at the left index. So we increase the left index, and vice versa. We decrease the right index. And the next question is, how do we specify this algorithm? So first of all, we have a precondition that constrains that the left and right index are actually valid indices into this array. This is fairly standard. And second, we have a post condition that ensures that the value at the result of this recursive procedure, which is denoted by \result here, is in fact the maximum of the subrange which we started out with. So the initial value of L and R of a particular recursive call. And I'm just presuming that this function max is somehow given in the library or whatever for presentation purposes. And yeah, this is the definition. So, but let me first point out that the post condition of a recursive procedure is in fact a relation, namely a relation between the result value and the original values of the parameters that we started with this particular call, right? So it's a relation here as well. And for that reason, I'm going to call it summary, because post condition is, in my opinion, not the appropriate word for that in the context of loops. So presume we have the consequence of this post condition or this equivalence, then it's very easy to use an SMT solver, for example, to prove that this algorithm is correct. And we don't need any additional annotations. The proof is fully automatic. And furthermore, this contract is sufficient in any calling context that we might imagine. So this is a complete specification and verification of this algorithm. Now, if we look at the iterative version, and this time let's try to prove it using an invariant. So let's go for the standard approach. Then we have an initial state. So this is typical in the challenges that you get with while loops. And we have replaced the recursive call just by inlining it to a side effect. And the invariant, if you look at it graphically, it says that this blue region between L and R in this array, so I'm using the upper index to be exclusively, right? It contains the maximum of the overall array, so of the entire array. So there is some index that is the maximum inside this blue region. And we can, of course, formalize it using maybe an existential quantifier. So we say that there is some k in the residual range that denotes the maximum of the entire array, right? And this is one of the possible formulations. You can do it in different ways. But again, we have that the proof using this invariant is fully automatic, and the post condition, which I have omitted here, but of course, it is also established by this invariant. So let's see what that means in comparison. Let me try the same. So like a loop is just equivalent to a tail recursive procedure, and we have seen both. And this also means that we can use the invariant to prove that the recursive procedure is correct. And if we do that, we get this kind of proof. And in particular, it means that if we use loop verification with invariants, then it corresponds to the tail recursive procedure where the precondition and the postcondition are the same. And that's a self-imposed limitation, right? So we are using a technology to verify loops that has a limitation, and there is no reason why we should not use the general form, right? And of course, this is perhaps reason for the belief that iterative algorithms are harder to verify. And to conclude this round trip, now what is missing is the proof for the iterative version using the pre and post condition approach. And let me first explain graphically how it works in this example. So we start into the loop at an arbitrary iteration, and we have this blue part of the array with our 2 pointers, and the summary that describes the residual operations is that we will end up, once the loop is finished, with some index, and I'm denoting it by L prime here, so that's supposed to be the final value of the variable L, that points to the maximum of this intermediate range. So the upper blue area, that is the, of this area, the maximum is denoted by L prime. And if we plug this into our iterative program, then we see that first of all, we are using a syntactic reference to the final value of L here in the ensures clause. And we also see that this summary is very, very similar to the post condition that I had omitted earlier, but which is shown on this slide. So, and we don't need the existential quantifier, for example. So I think this is a very nice and hopefully convincing example why in some examples having the flexibility to denote the precondition and the postcondition of a loop or the invariant and the summary separately gives you something in addition. So let me summarize what we've seen so far. Invariants, they describe the work done by a loop and up to a certain point, and they reason about partial results. And the summary of a loop contract describes the residual work that is still to do, and it reasons about complete results, so the complete maximum of some intermediate state, right? And so of course this is known, and let's now look into what this paper tries to achieve on top of this theory that is known. So first of all, I would like to present you a very simple, like the issue is that loop contracts are not really that well known in the community, at least that's my perception. And one aspect that I think ties into that is that I have not found a very simple formalization of the verification conditions. And that's what I'm going to explain next. So if we have a loop with precondition P and test T and body B and postcondition Q, and we would like to verify it using an invariant, then we do this. So we say initially the invariant is implied in state 0, so that I'm listing an execution trace where the states are the ones encountered at the loop head. And then we have these 3 classic verification conditions: initialization, propagation of the invariant over a single arbitrary iteration of the body, and then finally we establish the post condition in the final state. And note, of course, I'm assuming here that the loop test is satisfied in the intermediate states and it's not satisfied in the final state, but let's just keep that in mind. Now, with the summary approach, we are not doing this. We are in particular not using the last condition. We are not deriving the post condition directly from the invariant, but we do something else. We first summarize the whole execution of the loop by this binary relation R. So that's how we use the summary at the end. So we can say the over-approximation of the entire computation of the loop is given by R from S0 to Sn. And of course, then we can use the precondition to derive the postcondition. Now, the interesting bit is how do the verification conditions look like? So first of all, this summary, it propagates backwards. So it wraps up the whole execution after the fact and then justifies that the summary can be lifted from a summary of the very last state. So it has to hold reflexively in the last state. And then we can gradually move the first argument of R backwards over the individual iterations of the loop, right? So we get these two additional verification conditions. And if you want, you can also assume that the invariant has been proven to be an invariant, in fact, to help out, but it's not actually that necessary. So next, you can ask, what is the correspondence between invariants and summaries? And in particular, we know that proofs using invariants are supposed to be a complete method, right? So how do summaries tie into this picture? And the paper contains two results regarding this question. So the first result is that we can encode the canonical summary that we have seen on the first slide in this presentation, just by saying that the effect of the loop is explained by looking at the last state and stating that the invariant holds there and that the negated loop test holds also there. So we just completely ignore this facility of summaries to have this backwards propagating in first argument, and we just state what it holds in the last state. So this should also give you an intuition about how the proof of using invariants only does not use this backwards propagation mechanism, right? So it just goes forward, but not backwards again. And on the other hand, which is the more interesting bit, is that we can encode summaries as part of invariants. So for example, if we have a summary that has been proven to be correct using the proof obligations I have shown you, then we can state that we can construct an invariant that for a given state S translates like if we are given a summary of the residual iterations, then we are given a summary of the whole execution. So we predict that if the residual loop executes correctly, then we get a summary of the entire execution. And this existential quantifier for S0 is just to fix the initial state using the predicate P, and you can work around this. So, but let me first tell you what it means. So the first construction tells us that summaries are indeed a sort of complete way of verifying loops, because we can always plug in an invariant and we know there exists an invariant. So just as variants prove termination or decreasing orders, and invariants can prove functional correctness, summaries can also prove functional correctness of loops. But there is a small difference, so we still need invariants, and that's another result, to rule out errors that occur inside the body of the loop. So for example, out of memory, not out of memory, array out of bounds exceptions or something like that. These can still happen, and we need invariants to rule them out. And the converse encoding gives us a straightforward way to implement this method using loop contracts. So it tells us in particular that loop contracts are just front-end engineering. So I'm saying just because I know that tool engineering is a lot of work, but there is actually no excuse not to have loop contracts with loop summaries in your favorite verifier, because you can use this encoding. And if you're worried about the quantifiers, you can get rid of them in some situations. So for example, if you have the old keyword and you loop invariants, then you can get rid of this existential for S0. And if you have a functional dependency from some final variable, like we had for the max example, then you can collapse this implication and the universal quantifier gets eliminated as well. So what we have is a constructive translation that decouples the technical solution from the conceptual approach, right? And that's really the key insight here. We can say, I want to verify my loop using a loop summary, even if my tool only supports invariants. And in the worst case, I just have to do the manual encoding, right? But it gives us the justification to take loop summaries seriously as a specification, as a mechanism. So let's quickly look at the syntactic proof rule, because still you might want to say, I want direct support for loop contracts, right? I want to avoid this introduction of quantifiers in the first place. I want to implement verification support directly. And previously, so let me just go back to this. So this is the Hoare logic rule that I showed earlier, and I'm going to show the premises now for this rule, how you could encode them. And prior work, so for example, by Thomas Türk, did a trick that was feasible in the verification system he used. So he escaped to the meta level and treated Hoare triples as first-class syntax. And you don't need to do that. And so here are the two conditions. So you need one condition for the base case and one condition for the inductive case. The base case is actually trivial, and if you collapse this Hoare triple, then you will get exactly this, that R has to hold reflexively in the final state. But the first condition is somehow curious. So let's fix a logical variable xi that captures the state before executing the loop body once and then doing something fancy. And what we want to prove is that the residual iterations are abstracted by the summary R starting from xi. And we can express the fact that the residual iterations are supposed to be abstracted by the invariant and the summary by using a specification statement. So the specification statement is exactly what captures an arbitrary effect on the variables with a precondition and a postcondition. And that has been long known. And of course, verification tools support all the mechanics to encode such specification statements. Like, for example, you can write this down as assert I of x and then capture this state, the current state, using the variable xi plus 1, and then change the values of x to arbitrary values, and then proceed with assuming the R for the smaller state or for the next state, and then prove this R of xi and x. So you get exactly the same verification conditions out of that. And that said, is if you have these features in your verifier, then the implementation of this rule is very simple. So let me conclude with a few examples and a word on proof automation. So for example, binary search follows a similar pattern as the elimination, maximum by elimination. And here are an invariant that is, it's not the whole invariant, you still need the ranges of the indices, but this is the main part. And the typical invariant says something like that. The value we are looking for, x, in the array A is has not been found in the left half, and it also has not been found in the right half. And we're still making progress on the right, on the correct part of the array. Whereas the summary is much simpler. It just says that the result, so the indication whether this value is in the array or not, is just whether we can still find this element in this subrange. So this is much simpler. And in comparison, there are several cases where the summary captures the intention of the algorithm really well. So it's closer to the post condition, and that is reflected here. And we can also use these the second construction. So if we construct an invariant from this summary, then we get this very nice invariant. So we have to do a little bit of simplification, but this is a case where the universal quantifier can be eliminated, and we get this nice invariant that says, like, the effect of completing the loop is equivalent to looking into the original array. There's also a downside of using summaries. So for example, if we have a standard array copy program that has a loop using index I going from left to right and copying elements from A to B, then the invariant would state that the prefix starting from element 0 to element I has already been copied from the array A into the element array B, right? So we can say the two ranges are equal. Whereas the corresponding summary, it follows kind of a similar and symmetric idea. So it says that if I continue from now on, what will happen is that inside the array B prime, which denotes the final array, at least the array elements starting from the current index I to the end will have to be copied. However, we also need the fact that the residual iterations will not change the prefix again. And this is a more general issue with loop summaries. They are really bad at preserving information over the round trip to the final state and back. So in this example, the summary forgets that we had just set this element I in B to the value A of I, right? So they forget it. And that means that summaries may require additional framing. So here's a clear downside of this idea. And here's the last comparison, or the last major difference between invariants and summaries, namely that, so if you are using algebraic lists as part of your specification, then typically you would have some function f, which takes the current state and produces some sort of list that is supposed to represent a sub-range of the values in your array or something like that. That's very common. And algebraic lists are typically specified by manipulating the first element and doing some recursion. So, so there's a base case with the empty list and a recursive case for your specification function, which somehow follows the execution of the loop body, but the main point is that the first element is exposed. And this corresponds to a right-fold operation. And the insight is that invariants, they don't really match with this kind of definition, because invariants are inherently left-fold operations, whereas summaries are inherently right-fold operations, and they support this quite directly. And I think I have 1 minute left. Let me just point out that I think there is a lot of potential in using summaries and taking them seriously. For example, we have seen that in order to get the summary that proves the max by elimination, we just have to do a very simple generalization of the post condition. But unfortunately, that's too simple and it doesn't work well in more complex examples. And then in the extended version, you can also see some preliminary experiments using Horn solvers, but the results are not very conclusive. So let me wrap up. Thanks for your attention. Loop summaries consist of invariants and summaries, and they are sort of dual in nature, and they have complementary advantages and disadvantages. And the conclusion is that we really want both. And from this paper, you can take away that the theory and the tool is actually not that complicated. Thank you very much.
Great, thank you for the talk. I think we just about have time for one very quick question. So there's one question from Cody Rue at AWS. If the language is deterministic, can the contract relation always be made functional?
I presume yes. I think yes. However, the question is whether you gain significant abstraction by that, right? That's so it is possible, but it will complicate your proof later on if you take exactly the effect of the loop. Yeah.
Okay, cool. Cody also had a follow-up question, so you might want to chat to him afterwards.
Yeah, sure.